Saibao Algebra 2. That one's for you, Sebastian. We're not going to, we're all on the same page that I have no idea what it means, right? Cool. All right, so let's get chopped. Today we are starting 1.6. I don't know, chopped is bad, right? I assume. If one is chopped, is it bad? Okay, cool. Yeah, I follow a guy on Facebook that teaches middle school somewhere down south, and every week he takes track of what brain rot he hears. That's the big one down south this week, that apparently they're letting them all say it in school. I don't know. I heard that one person here says it. Why? I don't need my book. Okay, 1.6. We are talking today about what our bell ringer kind of introduced to us. We will be looking at systems. Now, very specifically, I'm going to review this a little bit slower than your book does, because your book launches in and says, let's just move on past everything that you've ever seen, but I don't think that's always the best approach. So, systems, and we're going to be looking at two types. This is going to take us a couple days to get through, but we're talking about systems of equations. And I'm going to show you a shorthand. I'll write the real word, but I want to see if you can get what it is before I write the whole word. Systems of equations and aniqua is what I write. What do you interpret this as? Inequalities, 100%. This is systems of equations and inequalities. Now, as we get going through, you guys probably remember bits and pieces of this from Algebra 1. When we're graphing inequalities, everybody's favorite thing to do is to shade the graphs. We will do all that and see where the overlap happens. I can't tell if Naomi just doesn't remember or if that face was just unrelated. Do you guys remember shading your graphs? Okay, so we'll see it again. If you don't remember, you'll be okay. But that's the inequality part. Let's start with systems of equations. So here we go, our first bullet point. Let's define what a system actually is. And we'll say system of equations. Okay, notice all caps, meaning this is a what? Indeed. Cool. So, by definition, systems of equations are super easy to just write down. We've actually seen a system already today. The bell ringer was a system of equations. All we're looking at is two or more equations. And we'll see later, they could be inequalities, but we'll deal with equations now. Two or more equations in the same variables. Okay, on your calculators, and I guess I didn't check you guys out calculators yet, but vars is my shorthand for variables. I will write variables here. I would encourage you to use vars, and the reason that I do this one is because on the fancy TI-84, there's a vars button that stands for variables. So, here we go. Two or more equations in the same variables. That means they can both be x and y, they can both be a and b. It doesn't matter what variables we use as long as there's two or more there. Now, what we care about is not only having the systems, and this chapter, or this section, for anybody who said we need more word problem stuff, there's a lot of them coming up in the second half of the section. That's not a threat, that's just mentally prep yourself. We'll do a bunch of them. But first thing I want to talk about with these systems is the solutions. Okay, we're going to learn a couple more Holloway shorthands today. Solutions. I will shorthand with my fancy SOL apostrophe N, my own Holloway contraction that I've made. Solutions to systems of equations is going to be our focus today. Now, there are several, at least, okay, there's two realistically ways that we can think about what a system of equations is. The way that we did it for the bell ringer, we looked very specifically at a solution that was purely graphical. Okay. What did I ask you to do on the bell ringer today? I gave you two equations that were both in x and y, and I asked you to find where they what? Where they intersect. That's it. For a graphical approach to systems of equations, all that we're going to look at is where graphs intersect. That's it. Why do I hate the purely graphical approach? What was the issue with the bell ringer today that made me not a big fan of graphical solving? Sonny, sure. Yeah, it could be, right? Like even if you graph perfectly, unless you have a super duper duper nice point, you're probably not going to get the exact right point. There's an issue there. Does that mean that it doesn't work to do it that way? No, absolutely not. It just means that maybe I don't trust it or don't want to spend that much time. Now, we can look where graphs intersect, or if you don't want to have to graph every time, what we'll do is an algebraic or an analytic approach. We'll use the word algebraic in here. Algebraic just means with algebra, right, Seabass? Cool. So an algebraic approach, we are looking for the same thing. We're going to get an ordered pair. That has to be what we spit out. But we're going to say the points, and I'm going to say point, and then I'll put an S here, meaning what? One more time. It could be one or it could be multiple, right? So we're just looking for the points that make each equation in our system true. And I think I just want to say each equation because it's obvious that we're talking about systems. Okay. Looking at this, there are very few times where I would ever suggest we do the purely graphical approach with a system of equations. Systems of inequalities, absolutely. That's what we will use for the bulk of it. But we want the algebraic approach, and that's what we're going to focus on today. Does all this, is it starting to ring more of a bell as we're talking about it? Okay. You guys looked in detail at two methods for solving systems of equations. And I know that, I don't know, I have vague memories of people coming in over the last couple of years from Russell's class talking about systems. Two methods. Does anybody remember one of them? Substitution. Okay, so we can solve by using substitution. So we'll use a little dash here. Substitution. And there's one more that we'll write here in a couple minutes, but I want to work through a substitution example or two first. Anybody remember the other one? Good word, not the one I'm after here.
Equality.
Elimination. Substitution and elimination are our two methods. Now, they will both work all of the time. There's never a right choice for which way you go, substitution or elimination. What there is some telltale signs that one of them is going to be way, way easier than the other. And if we can pick that out, we can make this as easy as possible for everybody. So we're going to get right in. And we'll use Desmos to check on our graphs after the fact. But we're just going to go right in. Instead of saying, here's our steps, we're going to do an example together. And then on the side, I'll write down the steps that we do. So we'll set it up. Let's do an example. And I suppose I'll do it the other way. We'll say step number. We'll go ahead and do the action or the operation, what we do. I'll just have it detailed in here. And we have our work that we'll actually work through with our problem. Okay, so trying to save time and combine these two. And I don't know if we really need that much space, but I'm just guessing. All right, let's get some problem here. So here's step one. Like this, not even step one, it's step zero. We need a problem to solve. So here is our system of equations that we're solving. We have a system that consists of two different equations. The first of these is going to be y equals 3x minus 1. And just to help us kind of sort stuff out, I'm going to switch color on mine, but obviously you don't have to. We also have y is equal to negative x plus 3. All right. As we look at this, could you graph it if I asked you to? Can I just get a thumbs up or thumbs down from everybody just so I can kind of see where you would place yourself for graphing these equations? Okay, so checking it out. Let's not graph it because I think there's a better way that we're going to trust the answer much more than we would have graphed anyway. Step one of solving a system of equations, and I'll do it like next to it. Step one, we want to solve either equation. And it could be, if we had three of these, we would say any, but solve either equation for a variable. Now, this one's nice. Because could we solve this equation for x or this equation for x if we wanted? Could we rearrange it and solve? We could. Or we could solve it for what? What do they both solve for already? They both have y equals, right? We've already solved them for y. That step has been done for you. So I'm just going to say done. We have them here, and this is a weird little annotation, but we'll say done in this problem. Because we've already solved this thing, or we didn't do it, but it was already solved for a variable. Okay, at this point, whether it was solved for us or we had to go through it, we now have something that says y equals or x equals. It's y equals in this case. I now need to do what? What's this method called? Substitution. So, here's what I'm going to think. I have this solved for y and this solved for y. These are the same y value, right? It's just y. Can I plug this expression in for this y, since we say that that is what y equals? So let's denote that then, or annotate that. Plug, so step 2, plug one variable into other equation. Now, when I say one variable, if we need to be specific, we solved for it. That's the one that we're plugging in. So in this example, and here's why I'm using that specific color coding, it doesn't really matter which one I plug into the other because they're both solved for y already. So I'm going to just plug this black expression, 3x minus 1, in for the blue y. And let's just see where it takes us. So here we go. I then, instead of this y, we're going to use this 3x minus 1. So let's do it. 3x minus 1 is now equal to what should we write on the other side? Negative x plus 3. Before we move on, questions at this point? Cool. I'm going to trust your algebra ability. I'm going to give you guys like a minute. I don't think we might need that much time. We might not. Solve this for x for me. If you need help with the algebra, I'm walking around not to get my steps for the day, but to make sure that I'm available to help with the algebra. Oh, one of you were wrong, huh? Ooh, I see your issue. How did you get rid of this x? This is minus x, right? Don't write minus 1, make it plus x. Okay. So we got 1. Cool. So coming around, I've glanced at a few pages. Seemingly x equals 1. Okay. So step 2 or step 3, if we want to just call it step, I'm going to add it to step 2. We solve for it. Solve for the other equation. That's solve for other variable. That's what we just did. Do you want to see my work to get x equals 1, or can I just dot, dot, dot and say x equals 1? Dot, 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 x equals 1. Super bold. Now, we're done, right? We solved for x, problem's over. No. Why? What are we actually looking for? We're looking for the point. Does a point only consist of x? No, it needs a y. So what I do, I always put a star here, not my answer, but I don't want to lose it in my work. Okay, I already heard a couple people tell me what the next step should be. What do you want me to write here for step 3 then? So we'll plug result from 2. Whoa, I don't know why I'm writing it here. Plug result from step 2. Where do I plug it in? Into which equation? Do I have to do both? Either, however you say it. Either equation and solve for the other variable. All right, so I will keep that there so we can see it. I can see my 2 equations up top still. Which equation should we plug into? The second one, says Lily. going to tend to agree with Lily. Why? It's easier. The numbers are smaller. Could we plug it into the top one instead? Yeah. Absolutely. Either one is fine. I'm going to elect, as Lily suggested, to plug it into the second one. So notice, our equation, and I will probably show more work than you guys, we had y equals negative x plus 3. But what did we just say we were going to plug in for that x value? Or we found x was? So here we go, negative 1. And I would normally put parentheses. In this case, it won't matter in the end. But I would encourage the parentheses because it'll help us avoid mistakes. What's negative 1 plus 3? So we get y equals 2. I'm going to star it. Awesome. We found x. We found y. Are we done? No. Not quite. We're close. Now, the cool thing about systems, and any system that you ever do, this will be true. If I give you, and rather when I give you a question about systems of equations on a quiz, on a test, it doesn't matter, you have the opportunity to know 100% if you are correct. Every single time. You never have to wonder if you're right. You can determine that. This, we said up above that if we're doing it algebraically, we're looking for the point or points that do what? That's graphical. I don't have a graph in front of me. What do we say about algebraically solving these? Makes each equation true. We have an x and we have a y. Let's check it. I'm gonna mental math this. I'm plugging it into each of these. What am I plugging for y? 2. So I'm claiming that 2 is equal to, let's just do some math. What's 3 times 1? 3. Minus 1? 2. 2 is equal to 2. Is that true? Yes. I'm good. Can I stop here? Yeah. You could. I would not recommend it because just because it's true in one does not guarantee it'll be true in the other. If it's a super ugly number, I understand that sometimes you might skip them, and I get that. I do the same. But these are easy numbers. Let's check both. This one, what's this y equal to? 2. 2. And let's just check. Is that the same thing as negative 1 plus 3? Yeah. Okay, were they both true? Yeah. I'm convinced then that our answer is 100% correct. When we do this then, we're just going to say, I'm not going to write it, but check answer. And then step 4, every single time, and I'm kind of a monster when it comes to notation stuff, write your answer as an ordered pair. Or if you'd rather, you can simply write point, ordered pair. Cool, which means, here we go. I always use bullet points for my answers, and I'll use bright red because it'll stand out. I'm convinced that my ordered pair was what? 1 for the x and 2 for the y. And look at that, we're done. Okay, now I imagine this probably is feeling a heck of a lot more familiar. Sweet. Okay, just to check, we had 3x minus 1 and negative x plus 3. Let's just check it out here. So we'll come over this way. Already forgot them. Negative x minus 3 plus 3. And the other one, 3x minus 1. Okay, here's what the graphs look like. And we just found 1, 2, right? Hey, look at that. We got it. This problem, I'm trying to think of how I want to word this. If I had asked you guys to graph this carefully, do you think this point would have been more likely to obtain? But, weird question. I think we can all agree in general what a nice number might look like. On the ordered or on the coordinate plane, are there more nice numbers or ugly numbers? Like, there's 1 and 2 and 3, those are nice, but then there's 0.672953 and 0.62956992, like 6, 7. All of those exist, right? There are so many more ugly numbers than there are nice numbers. Don't think that just because you get decimals or something at some point that you're wrong. That doesn't, odds are it's not going to be nice. Okay, I want you guys to do one on your own or with your neighbors. I will come around and kind of check. I'm going to give you guys a head start, but I want you to work one more problem for me. Before doing so, parts of this process that you looked at and went, I don't know what happened, and I was too shy to ask at that point in time. Okay. Exactly. Here we go. Check it out. I'm making up an example on the fly here, just so you're aware, which means what are the odds of them being super nice numbers? 0. I mean, I wouldn't say it's quite 0 because it could happen, but let's write some equations. I want 2x plus y equals 4. And let's say 3x plus 2y equals 20. I'm not going to get nice. We'll say 21. Cool. This problem, just right off the bat, to make sure all of our work looks the same, I just want to look at it. This one's fundamentally different starting point because step 1 is not done for me yet. We get to pick which equation we want to solve for which variable. Could I solve the bottom equation for x? Yeah. I could, but eventually I'm going to have to divide by 3, right? I can tell that I'm going to be in fraction land if I do that, so I probably wouldn't do that. Could I solve this one for x? Yeah. I'll have to divide everything by 2, so once again I'm in fraction land. Is there a better choice than solving for x? Yeah. I can solve for y instead. Which equation should I use to solve for y? Why? How come? Yeah, it's already 1y. Now, this first step, here's how I denote this, and this is a me thing. Most textbooks don't do it this way, but I have a way that I think helps us avoid mistakes. If we solve this for y, what would you do to each side? Subtract 2x. So check it out. Here's our step 1 already. Y is equal to, we could call it 4 minus 2x, but that feels clunky to me. I would call it negative 2x plus 4. We have step 1 together. We've all solved for y. I want you guys to run through the rest of this problem. I'm going to give us a couple minutes. I'll be walking around to answer questions and help as you need it. Let's meet up at the end. You shouldn't have to ask if your answer is right. Cool. I'm going to give you guys a head start. I'll start working it as well, but I want you a minute or two first. Cool. Notice, when we do this, there's a whole lot less writing than if we have to annotate all the steps out. This method, pretty convenient, and it works really well if you can solve for one equation, for one variable, without getting really gross numbers. Okay. Give me a thumbs up, thumbs down sort of indication to how you're feeling. Okay. Specifically about the math, just to be clear. Great with the math as well, Seabass? Yeah. Cool. All right. Well, substitution's pretty cool. What's our other method? Elimination. Okay, here's the deal. I don't think that we're going to finish all of this before the end of the hour. If we have to have like a half class of homework time to get some extra practice tomorrow in class, please don't cry too much about it. Cool. If instead of giving you homework, we just do some in school, like I get a lot of emails saying, please give us more homework all the way, like every day. Don't be too upset if that happens. Cool. All right. So substitution. Again, this is all the work that it takes. Check your answers. Let's move on to our second method. Okay, so we used substitution. We're also going to have elimination. Okay, the name is not like secret whatsoever. What do you think we're going to do with one of the variables? We're going to, yeah, sure, I'm fine with killing it. We're going to kill it. We're going to eliminate it somewhere in there. Now, remember, equations mean our scale is balanced, right? Okay, so if the scale is balanced, we're okay. If I double the weight over here, then I must do what over here? Double it. We just have to double it. When we're doing this, do you want annotations the same way we did the first one? Okay, I will offer the annotation stuff. You never have to do it. We're going to try to go a little bit quicker because are you guys feeling like you've seen all this before? Okay, so it is a good refresher, but maybe we don't have to teach it like it's the first time you've ever seen it. If you need it, let me know, but let's just jump in. We're going to do the same thing. We're just going to jump right in with an example. Here's the weird part of elimination. When we do elimination, I use a very, very specific notation that helps to like get rid of errors that people make. I would suggest you use it, but you don't have to write it down exactly like I do. Obviously you will this one, but I would always use this exact same format when doing these problems. So here we go. We'll just solve by elimination. And what I'll do instead of doing 2 columns this time is I'll do some little annotations in a different color so that if you want them, you can have them, but you don't have to. So, gosh, I've said so about 50 times today. I need a new word. What? Other than so. Ooh, it's not going to be that one. Just that one time is the only time you'll ever hear me say that word. All right. Anyway, 2x plus 3y equals 5. And we'll use green for the other one. Let's do 3x minus 4y equals 1. All right. My first question. What form are these equations in? Good. They're in standard form. Okay. Why is this not an obvious substitution problem?
Because it's not.
Okay. 30 seconds, talk with your neighbors. I'm going to call somebody random. Why is this not well suited for substitution as a question? Good. I like that. There's another way that we can think about it, but I agree with that. 5, 4, 3, 2, 1. All right. Number 5. I don't know who that is. My sheet's back there. Who's 5? Talia. Why do you think substitution's not going to be super nice here? The numbers won't be nice. Michael, I heard you say one word. Can you expand on that one word a little bit? Because I agree with you, just so you know. Why aren't the numbers nice? What does that mean? They're fractions.
Yeah.
What do you mean by that?
It doesn't divide well.
Yeah, if I tried to solve this for x, I'm going to wind up with a 5 over 2 and a 3 over 2. Because I'm going to have to divide by 2. If I try to solve it for y, I get 2 over 3 and 5 over 3 when I divide by 3. That's not very nice. The exact same thing happens here, which means maybe there's a better way. Okay, again, I want to stress, if I do something to the left side, I have to do it to the right side as well. And it doesn't change anything other than the way it looks. The expressions would be equivalent, meaning the exact same. They might look different, that's okay. We get to pick on which variable we want to eliminate first. Gut feeling on x or y? How come?
It's the smallest.
So you see a smaller number, I'm fine with that. I'll tell you, I would eliminate y's. That's what I would do, but either one is fine. I would choose y personally because what I'm going to do is I'm going to rewrite these equations here in just a second, and then we're going to add them. And I want stuff to cancel out. I see that y is positive and y is negative. Those will cancel out. But we could do the x's. How many of you would rather do the x's here for this first one? Cool, let's do x's. Everybody wants y's, let's do the x. So, I want to eliminate x's. I don't think you guys really wanted y. I couldn't get a read on you, but that's okay. Okay, I'm going to eliminate x. I need to make sure that this, whatever I multiply the entire top equation by and the bottom equation, I need these to cancel. Where's the first place that 2 and 3 meet? 6. Nope, not 7, just 6. What would you multiply both sides of this equation by to give myself a positive 6x? So if I multiply by 2, I get a 4x. I'm going to multiply by a positive 3. And here's how I'm going to denote it. This is times 3. Now, it's weird notation, and I get it, but what did I just say we're going to multiply by 3? Just the 2? Everything. So we have to distribute. Everything gets multiplied by 3. What's 2x times 3? 6x plus what's 3y times 3? 9y equals 15. Everything gets multiplied by 3. Now, for this next part, I'm not exactly sure how Russell or Jarvis taught this when you saw it. I will never tell you guys to subtract or do anything different. I want you to add every time. We avoid mistakes when that happens. If I want the x's to fall out, and I'm going to add straight down, what would I have to have here so that the x's completely fall out when I add them together? Everybody okay with a negative 6? We'll do that trick. What do I multiply the bottom equation by to ensure that I get a negative 6x? Negative 2. And what gets multiplied by negative 2? Everything. So here we go. I will have negative 2. And honestly, you could just write 3 here instead of the dot if your dash and multiplication symbol aren't the same. What is this equation going to be then? Negative 6x plus 8y equals negative 2. Questions with this step? King. So because we agreed as a class that we were going to eliminate the x's, if you didn't hear King, you said, where did the negative 2 come from? When we decided we want to get rid of the x's, were you cool with how we said, oh, they meet at 6?
Yeah.
Okay? And then I'm just going to look, as soon as I get a 6x up here, my only thought is, how do I make this turn into a negative 6x so that they'll fall out when I add them? So the question at hand was, what do you multiply 3x by to get it to be negative 6x? Almost.
2 and 3.
Just the bottom one. 3 times what is negative 6?
Times 2.
Almost. That's positive 6.
Negative 2.
There it is.
Oh.
Yep. Cool. All right. Now, these problems. My notation, again, looks different. I'm going to put a better bar than that. I'm going to put an equals bar. I don't know what this would actually be called. The bar that you do when you add stuff. I have no idea what it's called. Well, fraction bar is called a vinculum, so I have a feeling that this is probably the same thing. But anyway, let's add these together. Okay, I will put a obnoxious plus sign here, or add. This is like my annotation. Add these. Okay, so help me out. 6x, 0x. Do I have to write 0x? No. Nope. 9y plus 8y. 17y. 15 plus negative 2. 13. Awesome. This one is ugly numbers. I'm cool with it. Can we solve for y? For sure. What is y? 13/17. For those of you decimal lovers, what is this decimal real quick? Okay, so decimals are terrible. Agreed. I put a bullet point. I meant to do a star. We have a y value. Is that it? Is that all we need? No. What do we do? We get the x value as well. Now, for this part, I'm going to turn this to make sure it hears me. As we're looking at it, we have 2 equations originally, and then 2 equivalent equations. Any of these are fair game to plug into. It doesn't matter which one we pick. Choose the easiest. Fred, which equation up here, and I'll label these. Don't write it on yours, but we're going to do A, B, C, and D. Which equation do you want to plug y as 13/17 into? Into C? You said which one? D? Here's my suggestion. We can. And we could. I'm not going to, though. Because these are equivalent, right? These are just bigger numbers. They're the exact same thing. I would probably pick A or B. Which one has this easier thing to multiply y by? Negative 4 times 13/17? It doesn't really matter, right? Let's use B just for fun. Like, completely arbitrary. Just choosing. Okay, we are going to rewrite this with our new value of y. So here we go. That was our green one. We had 3x minus 4 times, I'm going to put something in there in just a second, still equal to what?
1.
I heard 3, I heard 5. I have no idea where those ones came from. I think it's 1, because I'm literally just rewriting this equation. Cool. What was y again? 13/17. Okay. No, they're both prime. But here's our decision we got to make. You guys can do fractions. Is it absolutely necessary that we do all of our work by hand? No. What might I suggest we do? Do you guys know how to use fraction stuff and make it nice on your calculators? Okay. Do me a favor. If you don't have one at your desk, grab me a calculator real quick. Like super quick. I also need one. You guys can share if we need to.
Alright, go.
Somebody probably has one that does not work. Sorry. If you have one that doesn't work currently, I'll see if one of these two works, because I also need one to be able to show you if it doesn't work.
We have to put it on the degree, right?
We don't have to change anything about that because we're not talking about angles. Can you share with somebody for a moment? Okay. just because I don't know where I put mine. All right, so here we go. Just to make sure we're all on the same page, we're going to finish this problem, and then we're pretty much done with class for today. So, 3x minus 4. Do you guys agree that I'm going to add whatever 4 times 13/17 is? Okay, so let's get this screen up here. All right, I already lost all my work, so I got to move this. Check it out. We're going to do 4 times 13/17 because that's our first part, yeah? 4 times 13 over 17. Okay, I get this awful decimal. But check it out. We are going to math frac this. That's the goal. There's a button on our calculator right here that says math. I haven't hit anything else. It's still just my ugly decimal. Hit math. What's the very first option in my math tab? Frac. I can hit 1 to enter that, or I can hit enter. I'm going to hit enter. And it'll say, hey, you want me to fraction this answer? I'm going to hit enter to say yes. And check it out. It's 52/17. Now, this can save time, but what we've just determined is this is 3x minus 52/17 equals 1 still. What would you do to solve for the algebra here?
Subtract.
You would subtract?
I mean, add.
What would you add?
Add 52/17.
So we would have 1 plus 52/17, right? Check it out. Here's 52/17 plus 1. I just switched the order around. And it's 69 over 17. Here we go. Quit it. 3x equals 69 over 17. One more step.
Divided by 3.
So here we are. Divide by 3. Oh, it's 23/17. Okay. This is that situation that we talked about. We will jump right in here tomorrow. On your way out, please, back on the desk, stack your folders. I didn't give you time to write the other piece today. Stack your folders so that they're all oriented the same way so I can just pick it up and put it in your file cabinet. Back desk here in the corner is fine with me. Calculators, just hang them up on your way out. So here we got the first one, and then when we look at the equation, I saw that this is where I was, and then we're going to add this to both sides of the equation. So just write plus 1, because it's going to be 1 plus 52/17. Yep, and then divide by 3. All right, later Raiders.
What's up, dog?
Not much. What's up with you?
You were spamming that last year.
No, I'm still gonna spam it now.